Last week we introduced a new concept called the mole, and we talked about how it is a grouping term used to talk about a really large number, because atoms are so tiny. We need a really large number to kind of make sense of them. And so we talked about how this mole, or amount of atoms, is equal to the mass of the average atomic mass for each element, and we call that the molar mass. But I haven't really told you what the number of particles is. We've just talked about the mole. And so this number, just like when we have a dozen, we're implying that there are 12. It is a ginormous number in a mole. And Avogadro is the scientist who linked the number of particles together with the concept of the mole. And so we call it Avogadro's number. And this number is referring to the particles, or, the stuff, the quantity, in 1 mole of a substance. And that particular amount is a very large number that we're going to write in scientific notation because it has so many zeros. If I were to write out all my zeros, I would have to have 23 of them. So we're going to put this in scientific notation: 6.02 times 10 to the 23rd power. Okay, so this is a number that we are going to need to be very familiar with and also good at putting into our calculator. So if you remember, when we did scientific notation, we used the little symbol capital E on your calculators. And this button, when it is on your screen, it will show up as just an E. But the button itself on your calculator is capital E. And this represents times 10 carat. Okay, so when you put it in your calculator, you'll type 6.02 and then hit the EE button. And then you can go right to typing 23. And so that will group it all together as one term in your calculator, making it easier to do calculations. Okay, so this word particles that we've talked about here, I wrote down, is referring to the number of atoms of an element or molecules of a compound. And sometimes they'll specify, even for an ionic compound, they'll call them formula units. But generally you'll see atoms or you'll see molecules. Atoms referring to elements, molecules referring to compounds. So with that being said, you'll have 6.02 times 10 to the 23rd power atoms in 1 mole of any element, and you'll have Avogadro's number of molecules in 1 mole of any given compound. And we can use Avogadro's number as a conversion factor. All of these 3 boxes up here are going to be our mole conversion factors, hence our name of the notes today, mole conversions. So our mole conversion factor of Avogadro's number is to say that 6.02 times 10 to the 23rd power particles, which again are atoms or molecules, equals 1 mole. So there's our conversion factor. I'm going to write that in stars. So 1 mole equals 6.02 times 10 to the 23rd power atoms of an element or molecules of a compound, depending on what you're working with. Notice in the example for amount, that's Avogadro's number. We're referring to amount here. You are finding molecules because CO2 is a compound. That's how it works. If I was just finding oxygen, then I would be finding atoms because it's an element. So that's how the relationship there works. Those are the types of particles, which is why I have or written there. It can be either one. So there's our amount. Let's do this example here before we look at molar volume. So it says how many molecules are in 0.715 moles of carbon dioxide. We know from this conversion factor we just found that 1 mole is 6.02 times 10 to the 23rd power. So if I have 0.715 moles, we're going to have, about 3/4, a little less than 3/4 of Avogadro's number. So let's put that into our calculator here and set up a conversion. Moles, and then since we're converting, we'll set up our little train tracks. And our new conversion factor here. Molecules in 1 mole of our compound. And then when you put this in your calculator, again, always start with the given, and then you're going to multiply by Avogadro's number using this E to help you shorten the numbers you have to put into your calculator, and you should get 4.30 times 10 to the 23rd molecules of CO2. And just like we predicted, it's a little less than Avogadro's number because it isn't quite a whole mole. So there's our answer for this one. The next conversion factor we're going to look at is for volume, which is going to give us the liters of a gas. And remember that volume represents the space that something takes up. And so if we have a gas that is taking up a certain amount of space, there are a couple of factors that affect a gas because it can be expanded or compressed. If you think about a balloon, you can squeeze it, or if you heat it up, maybe it'll expand even if you're not adding more particles to it. And so as a result, pressure and temperature are both going to be key players in the amount of space a gas takes up. And if we can keep those constant at a standard temperature and pressure, then our volume, or the space that the gas takes up, is going to remain constant, because it's not actually just dependent on how many particles per se, but it's dependent also on the temperature and pressure. So if we can keep those constant, then we can link the amount directly to the space or volume that it's taking up. So if we want to define this, again, we said the space is our volume. So this is our space. 1 mole of a gas takes up at standard temperature and pressure, which we shorten to STP. And for any given gas, that space is going to be equal to 22.4 liters if we keep the temperature and pressure at these certain standard conditions. And right here we have standard temperature and pressure. The conditions of that are 0 degrees Celsius, and that's freezing, so that would be 32 degrees Fahrenheit if you think about like when rain turns into snow. So there's our temperature, and then the pressure is just normal atmospheric pressure, 1 atmosphere. We haven't talked much about the units of pressure, but atmospheres are referring to the force that pushes down in a regular, the atmospheric pressure. So 1 atmosphere is considered our standard pressure. So if your conditions are 0 degrees Celsius and 1 atmosphere pressure, then you can be assured that 1 mole equals 22.4 liters of that particular gas. So let's do the volume example here, which is our third one. How many liters now of gas are in 0.715 moles, same amount of carbon dioxide? So now this time, since it does say at STP, we can use our volume conversion factor. So we always have 22.4 liters of a gas. And if we plug that into our calculators, we will get 16.0 liters of carbon dioxide. And again, that should make sense because we don't have quite a full mole. So it makes sense that we have a little less than 3/4 of a full mole of gas. And then our third mole conversion, let's write the conversion factor here for volume. 1 mole equals 22.4 liters of a gas at STP. can use that to convert between moles and liters of a gas. And if you ever need to find milliliters, just remember the metric conversion. You have an additional conversion factor that you know that 1,000 milliliters is equal to 1 liter. So you can also use that to help you convert to milliliters. Our third conversion factor we introduced last week, and I've written it here again so that we can see all three of our mole conversions side by side. And this is molar mass, and that we defined as the mass of 1 mole of a substance equal to the average atomic mass for the elements on the periodic table. And if you're finding the molar mass of a substance, you add the sum of all of its atoms, and we can use molar mass to convert between grams and moles. So our conversion factor here is 1 mole equals the molar mass of your compound or element. And that varies. So notice the two we introduced today are fixed. They will always be constant, that a mole is always 6.02 times 10 to the 23rd power atoms or molecules, and it's always 22.4 liters of a gas at standard temperature and pressure. However, last week we saw molar mass changes because each element has a different mass. So that's why it just says molar mass. It depends on what compound or element you have working with. So let's do this third example. Same amount, but we're going to see how we have a different volume and mass as we're working through these. So our molar mass of carbon dioxide, you'll need to add those up from your periodic table. So just to review, carbon is 12.01, oxygen is 16, and you have 2 of them. So our total there is 44.01 grams. And we use that as our conversion factor. Now our answer, if we plug this into the calculator, is 31.5 grams of carbon dioxide. So all of these represent 0.715 moles of carbon dioxide, just written in different units: molecules, grams, and liters. We have a picture here just kind of summarizing what we've talked about, that all of these have 1 mole, which would be the same amount of particles, 6.02 times 10 to the 23rd power, atoms for helium, molecules for oxygen and carbon dioxide. They have a different molar mass because of the periodic table masses, and they have the same volume because they are all at standard temperature and pressure, even though they're different gases.